Hello class, this is Mrs. Ayodeji with today's video on section 10.3, Finding and Using Taylor Series. As you're watching the video, please remember to write down important vocabulary, formulas, equations, examples, and graphs. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what is occurring. And at the conclusion of watching the video, write a brief summary of what occurred in the video in your notes and submit that summary via the online WISC the day before class. All right, let's begin. We've been working with Taylor series, and a couple of questions that came up from the WISC we're going to actually answer regarding Taylor series. So let's review about Taylor series. Here's the general form of a Taylor series of a function f of x about a point x equals a. And really the most difficult part of determining a Taylor series for a function is actually determining the coefficients of the series. And the coefficients of the series is all about finding the derivatives of the function. And for simple functions, the derivative and multiple derivatives are easy to find, but what if it's not such a simple function? And so we're going to look at some strategies to use to be able to do that. Okay, let's begin. So we know, for example, we have e to the x, and that's simple enough. We've learned that, I think that's part of your foldable. But what if I have something that involves e to the negative x squared? Well, in order to determine the Taylor series for this, we need to determine the derivatives of this function. Well, the first derivative will be negative 2x e to the negative x squared from the chain rule, and the second derivative we'll have to use the product rule to be able to determine that. And that's just for the first two derivatives. If we go even further for the third derivative, we're going to be doing a combination of chain rule and product rules, and it just takes up a lot of time to be able to determine the Taylor series using this method. But if you recall, let's just change the variables, and in this case, let's make instead of x, y, and e to the y is this Taylor series about y equals 0. And let's just substitute, instead of y, substitute negative x squared. And when we do that, we essentially get this. And then that means that the Taylor series for this actual formula or function can be found to be simply this by doing simplification. Why can we do that? Well, the Taylor series for e to the y involves only powers of y, not derivatives of y. It only involves the powers of y. So if y in this case is negative x squared, then it's going to really only involve, the Taylor series is only going to involve the powers of negative x squared. And so this is a much simpler and quicker way of computing the Taylor series for e to the negative x squared than by doing the long way and find the derivative for each term of e to the negative x squared. So that's one strategy. And let's see if we can use that for another problem. Example 1 is finding the Taylor series about x equals 0 for f of x equals 1 over 1 plus x squared. Well, we remember that from the binomial series, it looks like this, and since in our case p is equal to -1, then we have something that looks like this, and we're going to use y instead of x. And in this case, for 1 over 1 plus y, the binomial series looks like this. Okay, we did this a couple of days ago. Well, again, let's substitute x squared in for y, since the Taylor series for 1 over 1 plus y only involves the powers of y, and then we end up with this expression, since y is equal to x squared. Okay? Again, a strategy that allows us to get around all the difficult computation and make life easier, because that's what mathematicians like to do. Now, one of the questions that came up in one of the WISC about Taylor series is, if we have a Taylor series approximation of a function, can we differentiate it or integrate it, and will the derivatives and integration be the same as the Taylor series? And the answer is, of course, yes. But again, we have to be careful, because remember, the Taylor series is only equal to the function values around small intervals about x equals a. So it's not in general, but it will work as long as your limits of integration are within the small intervals for which the Taylor series is exactly equal to the function. So let's look at an example over here. We have 1 over 1 minus x squared. We want to find the Taylor series about this. Well, we don't have any useful strategies. Of course, we could use the power series for p equals 2. But again, that will involve a lot of different derivatives. Why can't we take advantage of the fact that we already have the Taylor series approximation about the Taylor series about x equals 0 as a function? And so the derivative of 1 over 1 minus x is equal to 1 over 1 minus x to the power of 2. Well, we know what 1 over 1 minus x is according to its Taylor series approximation, and we end up with this for x values between -1 and 1. So for x values between -1 and 1, if I take the derivative of both sides, then I will get the Taylor series approximation for the derivative, which ends up being 1 over 1 minus x to the power of 2, and we get something that looks like this. So in other words, now we have a way of determining, using and taking advantage of the derivative of a known Taylor series, so we can be able to easily find the Taylor series function for that function. Okay, so the trick is you have to recognize whether or not the derivative of the function you're looking at is something we already know. Same sense of for the integration of a function. Let's try 1 over 1 plus x squared. If you don't know this or not, but the antiderivative of 1 over 1 plus x squared is arctan. So the derivative of arctan can be found by taking the derivative of the Taylor series for values around x equals 0. In this case, from x values from -1 to 1. And so then I integrate both sides, and then I end up with this Taylor series, which will give you the value for arctan of x for x values close. Now, the thing I want to point out is that in this case, we have a c value, and the question is, well, what is c going to be? Well, in this case, c is going to be 0, and the reason why c is going to be 0 is the arctan of 0 is exactly 0, so we're not going to have a numeric value. So this is our final answer, because the c is equal to 0 for arctan of x values close to 0. Okay. All right, another question that came up, oh no, this one didn't come up, but how can we also use Taylor series to make life simpler if we're trying to find Taylor series of more detailed functions? Well, we can multiply and substitute. So here we have, of course, the Taylor series for sine of x, which I forget who did that. I think that was either John or Rick. I can't recall whose function that was, but it's on your foldable. But what if I wanted to find the Taylor series for the function x squared times sine of x? All I have to do is multiply x squared times the Taylor series of sine of x, and I simply get this expression. Real easy. So why go through the process of trying to find the derivatives of this complex function when we can take advantage of the fact that we already have a Taylor series for sine of x and use that to our advantage? What about, in this case, find the Taylor series about x equals 0 for g of x equals sine of x times cosine of x? Well, we know what the Taylor series for sine of x and the Taylor series for cosine of x is. So the one strategy we're going to look at is use those Taylor series and multiply them together. And when we do that, we end up with something that looks like this. Well, we can't really determine what the Taylor series is of this. We just know the terms that are part of it. So we try and figure out an organized way to list the powers of x in this product. Well, first of all, let's go and say, well, the constant term, there is no constant term because x times 1 is the lowest power term of x. So we don't have a constant term. Our linear term, our x power, is just found by multiplying x times 1. We have no quadratic term because there's no x to the 1 term being multiplied by x to the 1 term. So we have no quadratic terms. And in fact, we won't have any even power terms because you're always multiplying a even power term by an odd power term, which will always end up not being an even power term. So actually, we don't have any even power terms in this Taylor series. But let's take a look at the cubic term. Now, there's two cubic terms are involved: x times an x squared, and then there's an x to the third, times 1. So when we combine these together and simplify them and add them up, we end up with our x term of negative 2x to the third. Okay. Well, that can be very tedious, but let's try it for another term. Remember, there's no quintic term. And when you try it for, let's say, the nth term, as long as n is odd, we're going to see a pattern occurring. And this pattern looks something like this. And you can figure out the term the x to the 7th term, you can figure out it should be a negative, and then it's going to be a 2 over a 3 times 5 times 7 and times x to the 7th. But again, this is a strategy, a little bit more work than we would like. If there's an easier way, let's try it. And there is an easier way. We can use what we remember about trig identities, that sine x cosine x is the same as 1/2 sine of 2x. So since I already know what the Taylor series is for sine of x, I can use substitution to figure out the Taylor series for the sine of 2x, and we get that. And then I multiply it times 1/2, and we end up with this as our answer, which would give us the same as this as well, just this is a quicker way. So there are easier ways of determining the Taylor series than actually going through and differentiating the function multiple times, okay? All right, the last thing we're going to do is based off a question that you had was how can we use the Taylor series? And I'm going to go over two examples about how we can use Taylor series. The first one is you can use it to estimate a value. In this case, we're going to use the Taylor series of arctan of x to estimate the numerical value of pi. So we know that the tangent of pi over 4 is 1. So the arctangent of 1 is pi over 4. We also know that, so therefore, if I multiply both sides by 4, I get that we have pi is equal to 4 times the arctangent of 1. And I already have determined the Taylor series for the arctangent function of an x, arctangent function of arctangent of x where x is 1. And we end up with something like this. And so it simply can be found using a table of values for partial sums. Let's say S sub n represents the nth degree polynomial term of a Taylor polynomial. So for n equals 4, we get this is our S sub n, n equals 5. It's increasing very slowly, but as we get all the way to 1,000, we start seeing 3.141, 10,000, 3.141. So we can start estimating pi based off the arctangent. Cool, isn't it? It is. It is to me. Okay, the next example is we can also use Taylor series to determine which function is larger, as the function in this case nears to 0. E to the t and 1 over 1 minus t look very similar around x equals 0, but which was actually larger? And if we didn't have a graph or graphing mechanisms, we can use Taylor series to figure that out, because we do know what the Taylor series for e to the t is, and we do know what the Taylor series for e to the for 1 over 1 minus t, and they look very similar. But if you notice, they share the same the 1 plus t term, but then after that they go differently. And so really to determine which values are greater, we need to be comparing the terms after 1 plus t. And we can compare them together. So in this case, the t squared term is a larger term than the t squared divided by 2 factorial. In this case, the t to the cube term is larger than the t cube over 3 factorial term, and that will continue since that's how the format of the series goes. We can compare the general term and see the same result. So that lets us know that in this case, e to the t is going to be always less than 1 over 1 minus t for t values between -1 and 1 for which the Taylor series is defined. There's also another example in the book, but I'm not going to go over that for the interest of time. But this video is a lot of examples and for strategies for quickly finding the Taylor series of complicated functions. So I hope you enjoyed it. See you in class.